Right. The next subtopic under shaft power cycle is design point performance calculations. So we will look into examples of the calculation involved in the shaft power cycles. In shaft power cycle, we have ideal cycles, methods of accounting for component losses, and for now, for this particular presentation, we will look into design point performance calculations, and later we will look into comparative performance of practical cycles, combined cycle and cogeneration scheme, and closed cycle gas turbine. Okay, so for this one, before assessing the effect of component losses on the general performance curve for the various cycle considered in our previous section, which is section 2.1, the ideal cycle. So it is necessary to outline the method of calculating the performance in any particular case for specified values of the design parameters. So remember the design flow chart in the chapter 1 as well. So these parameters will include the compressor pressure ratio. Okay, we have the compressor pressure ratio. Okay, the first one, turbine inlet temperature, TIT, the component efficiencies, and pressure losses. So we have many components that we have to look into, and we also have going to include the turbine inlet temperature, the compression ratio, as well as the pressure losses in our design point performance calculation. Several examples will be used to show how these effects are incorporated in realistic cycle calculations. For the first example, so we have 3 examples altogether. So for this particular presentation, we will look into the first one. We consider a single shaft unit with a heat exchanger and using modest values of pressure ratio and turbine inlet temperature and typical isentropic efficiencies. Looking into the first one, so we have a typical heat exchange cycle. So we have the compressor, we have the turbine, we also have the combustion chamber and the heat exchanger. So you need to determine the specific work output. Okay, that's the first one. We need to also determine the specific fuel consumption, SFC. We also need to determine the cycle efficiency for a heat exchange cycle in this particular figure. Okay, let us go through the parameters that provided in this example. The heat exchange cycle having the following specifications: the compressor pressure ratio of 4.0, turbine inlet temperature of 1100 Kelvin, isentropic efficiency of the compressor zeta C, and then given as 0.85, isentropic efficiency for the turbine zeta T 0.87, mechanical transmission efficiency zeta M 0.99, combustion efficiency zeta B 0.98, and heat exchanger effectiveness 0.80. Right? They also provide us the pressure losses, combustion chamber pressure losses, PB, delta PB, 2% of the compressor delivery pressure, okay, and heat exchanger air side as delta PHA. A stand for air side, 3% of compressor delivery pressure, and heat exchanger gas side delta PHG, and the gas side 0.04 bar, and given the ambient condition PA and TA to be 1 bar and 288 Kelvin. So those are the parameters, the following specification for the heat exchange cycle. Let us try to calculate one by one. So since TO1, okay, the temperature at the inlet of the compressor equal to the ambient temperature, and the pressure at the inlet equal to the ambient pressure, and air is the operating fluid okay, where gamma, the specific heat ratio is 1.4. And the temperature equivalent of the compressor work is given in equation 211. This is equation 211, right? Where we will get the value of TO2, okay? And then the turbine work is WTC, required to drive compressor per unit mass flow. We can also we use the corresponding equation that we have already worked out in our previous classes, right? And putting the value for CP, specific heat capacity for air, at constant pressure 1.005, the TO2 minus TA, which is equal to 164.7, okay, and the given mechanical efficiency, the transmission efficiency of 0.99, you will get work for the turbine required to drive the compressor is 1.67.2 kilojoule per kilogram, right? And then you find the PO3, okay, by having this expression, okay, where note that the value of pressure losses at the burner, okay, the combustion chamber 0.02, and the change of pressure at the heat exchanger at the air side 0.03, you will get the PO3 to be 3.8 bar. And then you continue to calculate the PO4 pressure at the turbine to be 1.04 bar, and finally you get PO3 over PO4 equal to 3.654, right? So following through, so since at the turbine, okay, the gas is already coming up from the combustion product. It's no longer 1.4. It's already now it is 1.33. Okay, so you have to take note on this value. Okay, it is at the gas 1.33 for the specific heat ratio. For the expanding gases, the temperature equivalent of the total turbine work from equation 2.13, right? So you can use equation 2.13 to calculate the TO3 minus TO4, which is equivalent to 264.8 Kelvin, right? So the total turbine work per unit mass flow that we can now calculate, okay, for CPG, okay, the CPG, the 1.148, right, the given already, and then you will get the turbine work flow, turbine work per unit mass flow is 304 kilojoule per kilogram. So remembering that the mass flow is to be assumed the same throughout the unit. This is our assumption. So the specific output is simply as WT minus WTC. So just now we already calculate the turbine work per unit mass flow, and work by turbine and compressor is already calculated earlier, right? And you will get the difference between the two to be 136.8 kilojoule per kilogram, right? So it follows that for a 1000 kilowatt plant, and air mass flow, the m dot to be 7.3 kilogram per second. So this the m dot here is 7.3 kilogram per second would be required. To find the fuel air ratio, we must first calculate the combustion temperature rise from the turbine inlet, okay, to the turbine outlet. So from equation 2.22, the heat exchanger effectiveness, this is given already, okay, heat exchanger effectiveness of 0.80, okay, the temperature TO5 minus TO2 over TO4 minus TO2, where we already know TO2 to be 452.7 Kelvin, and TO4 is 835.2 Kelvin. Then you may calculate the temperature rise of the combustion, right? Okay, hence you will get TO5, right? TO5, which is 758.7 Kelvin. So from figure 2.17, for a combustion chamber inlet temperature of 759 Kelvin and a combustion temperature rise of 1100 minus 759 Kelvin, which equivalent to 341 Kelvin. That is the combustion temperature rise. And the theoretical fuel to air ratio is given as 0.094. So let us just look at the chart of figure 2.17, combustion temperature rise versus fuel to air ratio, right? So basically this is the figure that we have looked in our previous lecture. So this axis, combustion temperature rise, assuming complete combustion from 150 Kelvin to 950 Kelvin, and we have the fuel to air ratio from 0.04 to 0.014 for the bottom part of the chart, and from the top part of the chart we have the other values. So let us zoom in into the corresponding values. Okay, looking into the values that we already obtained earlier, 341 Kelvin at the combustion temperature rise, and equivalent values for the inlet air temperature, right? So you will get a value of the fuel to air ratio, okay, which is corresponding to 0.094. It's quite difficult to get it as accurate as possible, right? But as long as you get it to be plus minus a few percent, okay, 5 to 10%, it is acceptable. Okay, of course, this is very accurate, 0.09, okay, 0.09, 0.010. So it is roughly around there, where this small box equivalent to 0.091, 92, 93, and 94. Okay, and the most hardest part is to get the correct value for the inlet air temperature, right? So from this particular graph, we can now calculate the true value of the fuel to air ratio, which is resulted to be 0.096, and you put into the specific fuel consumption equation, and we already obtained the difference between the work done by the turbine and work done by the turbine and compressor, which is equivalent to 0.253 kilogram per kilowatt hour. Finally, cycle efficiency can be obtained to be 0.331, which is very low, 0.331 for the heat exchange cycle. A modern engine would operate at a significantly higher turbine inlet temperature. Okay, so imagine that a higher turbine inlet temperature, and this in turn would require the use of a higher pressure. So if you repeat the calculation with a pressure ratio of 10, right, and a temperature of 1450 Kelvin, it will result in an increase of a specific output by 115%, and the cycle efficiency is raised to 31.1%. Right? I would like you to try to use the same approach for example 2.1, okay, and use a pressure ratio of 10 instead of pressure ratio of 4. In this example, we use pressure ratio of 4 and a lower temperature. So we have now a higher temperature, turbine inlet temperature of 1450 Kelvin, and you will see that the cycle efficiency is already raised to 39.1%. It's not that significant, but it is sufficient enough. Okay, so that is basically the example number 1. Now example number 1 that I would like to share with you. Okay, so to continue, let me just try to open example number 2. Yes, this is the one. Okay, for example number 2, okay, earlier example 2.1, we have the heat exchange cycle. Now we have a free turbine unit. Okay, you can see here we have a power turbine. So determine the specific work output, specific fuel consumption, and cycle efficiency for a simple gas turbine with a free power turbine, figure 2.21. It has the following specification: compressor pressure ratio 12, turbine inlet temperature 1350 Kelvin, isentropic efficiency zeta C 0.86, isentropic efficiency for each turbine. There are 2 turbines. Okay, turbine number 1 0.89, turbine number 2 also 0.89. Mechanical efficiency of each shaft, okay, 0.99. Combustion efficiency given 0.99. Combustion chamber pressure loss is 6% compressor delivery pressure. Exhaust pressure loss 0.03, and the ambient pressure and temperature to be 1 bar and 288 Kelvin. The same approach we in the previous example 2.1, okay, you will obtain the corresponding value for the temperature difference between the compressor outlet and compressor inlet to be 346.3 Kelvin, right? And specific work for the compressor, okay, and to be 351.5 kilojoule per kilogram, and the pressure at the outlet of the compressor, 11.28 bar. So you will be able to do the same approach as the previous example. Okay, the intermediate pressure between the 2 turbines, PO4, is unknown, but can be determined from the fact that the compressor turbine produces just sufficient work to drive the compressor. The temperature equivalent of the compressor turbine work is therefore can be obtained, and the temperature difference here, okay, is 306.2 Kelvin. You input the values of the compressor turbine work just now. We have already calculated it, and then we also have the value of the specific heat capacity at constant pressure for the gas combustion product 1.148. Okay, and then the corresponding pressure ratio can be found using equation 212, where you have the corresponding pressure ratio, right, for PO3 over PO4 to be 3.243. Okay, and you will then obtain the value for temperature inlet, turbine inlet temperature, TO4, to be 1043.8 Kelvin. The pressure at entry to the power turbine, PO4, is then found to be this value, 3.478 bar, and the power turbine pressure ratio is 3.377. Okay, that is the power turbine pressure ratio. The temperature drop in the power turbine can now be obtained from equation 212 as here, TO4 minus TO5, which is equivalent to 243.7 Kelvin, and the specific work output for the power turbine, TP power turbine, which is equivalent to 277.0 Kelvin, kilojoule per kilogram. Right. Now, using the same figure, figure 2.17, we have to use the compressor delivery temperature, all right, as 634.3 Kelvin, and the combustion temperature rise as 715.7 Kelvin, which resulted to give us the theoretical fuel air ratio to be 0.0202 value. And from there, we can then calculate the actual fuel to air ratio. Just now, from the table is theoretical value. The actual value is 0.0204. So we see here from table 2.17, okay, with the corresponding value of the combustion temperature rise as well as the inlet air temperature, you will get the theoretical fuel to air ratio to be 0.0202, right? And then you calculate the specific fuel consumption and the cycle efficiency as the same equation, which resulted to the SFC 0.265 kilogram per kilowatt hour, and the efficiency for the cycle with the power turbine to be 0.315, right? So to discuss about it, it should be noted that the cycle calculation have been carried out as above to determine the overall performance. It is important to realize, however, that they also provide information that is needed by other groups such as the aerodynamic and control design group. Remember when we look at the design procedure, section 1.9, the chapter 1.9, where we also need to consider other factors from other design group, the aerodynamic and control design group, right? The temperature at entry to the power turbine, okay, TO4 for example, may be required as a control parameter to prevent operation above the metallurgical limiting temperature of the compressor turbine, right? So as we discussed earlier about the importance of the cooling bleeds, bleed flow, the exhaust gas temperature, EGT, of TO5 going into the nozzle would be important if the gas turbine were to be considered for combined cycle or cogeneration plant, right? Which were first mentioned in our first chapter, and also will be discussed in the later section 2.5. For the cycle of example 2.2, okay, as we have gone through just now, the TO5 value, which is 800.1 Kelvin or equivalent to 527 degrees Celsius, which is suitable for use with a waste heat boiler, right? When thinking of combined cycle plant, a higher turbine inlet temperature might be desirable because there would be a consequential increase in the exhaust gas temperature or TO5, permitting the use of a higher steam temperature and a more steam cycle. So if the cycle pressure ratio were increased to increase the efficiency of the gas cycle, however, the exhaust gas temperature would be decreased, resulting in a lower steam cycle efficiency. Right? The next example, example 2.3, will illustrate how the need to make a gas turbine suitable for more than one application and can affect the choice of the cycle parameters. Right? So that leads us to the example number 3. Example 2.3 now. We have looked into heat exchange cycle and then the power turbine cycle. Now we consider the design of a higher pressure ratio. Higher pressure ratio, single shaft cycle with reheat at some point in the expansion when used either as a separate unit or as a part of a combined cycle. The power required is 240 megawatt at 288 Kelvin and 1.01 bar, right? So the plant is shown here, a reheat cycle. Okay, you have Where is the mouse? I cannot see the mouse. Okay, maybe it is there somewhere. Just okay, it's there. Right, we have a reheat cycle. We have two combustion chamber instead of just one. And previous, instead of one combustion chamber, and we have high pressure turbine and low pressure turbine with only one compressor. A heat exchanger is not used in this particular example because it would result in an exhaust temperature that would be too low for the use with high efficiency steam cycle, right? So this particular cycle, reheat cycle, having the following specification: compressor pressure ratio of 30, polytropic efficiency for the compressor and the turbine is 0.89. Turbine inlet temperature for both turbines, since we have two turbine, high pressure turbine and low pressure turbine, in the temperature of 1525 Kelvin, right? The change in pressure ratio for the first combustor is 0.02, and for the second combustor is 0.04. Exhaust pressure given 1.02 bar. Okay, in order for us to perform the calculation, to do the analysis, we have to simplify the calculation. That we assume that the mass flow is constant throughout, right? So from the compressor until the end, the mass flow m dot is the same, ignoring the effect of substantially cooling bleeds, right? Remember, we have less than 1% of cooling effect, so that would be required with the high temperature inlet temperature specified, because we have 1500 degrees Kelvin of turbine inlet temperature, which is quite substantial. The reheat pressure is not specified, but as a starting point, it is reasonable to use the value giving the same pressure ratio in each turbine. So as shown in section 2.1, so this division of the expansion leads to equal work in the turbine, the both turbine, high pressure turbine and low pressure turbine, and a maximum net work output for the ideal reheat cycle. Right, it is convenient to start by evaluating n-1, okay, greater than n for the polytropic compression as well as the expansion. So referring to equation that we have already gone through before, equation 219 and 220, we have the following result for compression, okay, 0.321, and expansion 0.223, okay. And then making the use of a usual assumption that the ambient pressure equal to PO1 and ambient temperature equal to TO1, we will have the corresponding value of TO2, right? And the difference between TO2 and TO1, which is 570.1 Kelvin. You will later get the value of pressure at station 2, right, 30.3 bar, and station 3, 29.69 bar by inserting the values, and finally station 6, 1.02 bar, and you have a pressure ratio of PO3 over PO6 to be 29.11, right? Theoretically, the optimum pressure ratio for each turbine would be equal to 5.395. So the 4% pressure loss in the reheat combustor has to be considered, so as a value of 5.3 for the pressure ratio of PO3 over PO4 could be assumed. Okay, then you will get the temperature ratio of TO3 over TO4, and you will get TO4 to be 1052.6 Kelvin, and the pressure at PO4 to be 5.602 bar. Okay, and then to continue, you will then calculate PO5 and then get the pressure ratio PO5 over PO6, and then get the corresponding value of T temperature ratio of TO5 to TO6 and obtain the value of TO6. Okay? Assuming unit flow of 1 kilogram per second and a mechanical efficiency zeta m 0.99, you will get the turbine output, okay, to be this value, and the compressor input WC to be this value. And then the net work output is basically you subtract the values of the turbine work output and the compressor work input. You will get the net work output to be 499.3 Kelvin, right? I think I'm going backward. Okay, and the flow required as given in the question is 240 megawatt. Okay, and you will then get the mass flow rate to be 480.6 kilogram per second. Right. Then we want to continue to use the figure 2.17. Right. We have the combustion temperature rise 667 Kelvin and the inlet temperature of 858 Kelvin. Right. From figure 2.17 you will get 0.0197. Okay. Since we have two combustor, right, for the second combustor we will get a value of 0.0142. Okay, let us see how to use the chart. Okay, for the first combustor, right, we get the value of the combustion temperature rise and the inlet air temperature. You will get 0.0197. As I said, if you couldn't get the exact value, you may get the value corresponding to it, and maybe 0.20 or 0.19 would be acceptable in those range. And then the other one, the second combustor, okay, by putting the value here, right, value for the combustion temperature rise and the inlet air temperature, you will get the corresponding value of 0.0142 for the theoretical fuel to air ratio, right? And from the theoretical fuel to air ratio, we then for the both combustor and combustor number 1 and combustor number 2, then we will get the divided by the efficiency of the combustion chamber 0.99, we will get the true value of the fuel to air ratio, which is 0.0342 for both combustion chamber. And then you will get the thermal efficiency for the cycle, the heat cycle, to be 33.9%. So, what's the conclusion? This is a reasonable efficiency for a simple cycle operation. Okay, and the specific output is excellent. Examination of the temperature at the turbine exit, however, shows that the value is around 1053.8 Kelvin. And this temperature is too high for efficient use in a combined cycle plant. Right? A reheat steam cycle using conventional steam temperature of about around 550 to 575 degrees Celsius would require a turbine exit temperature of only 600 degrees Celsius. And this 780 degrees Celsius is a bit too high. And the temperature, and the turbine exit temperature, the TET, turbine exit temperature, could be reduced by increasing the reheat pressure. Right, the second combustion chamber, you have a slightly higher pressure. If the calculation are repeated for a range of reheat pressure, the result shown in figure 2.23 will be obtained. Okay, so if we continue to try to iterate in terms of putting a different reheat pressure of from range from 4 to 14, you will see that the exhaust gas temperature will be reducing. The efficiency obviously will be reduced. It can be seen that a reheat pressure of 13 bar, okay, reheat pressure of here 13 bar, give an exhaust gas temperature of 605. So let me just point it out using using a pen. Okay, so let's say this is at 13 bar. Okay, so it will result to be a 605, 605 degrees Celsius of exhaust gas temperature. So the specific output is about 10% lower. And oops, let me just go back. All right, 10% lower. Earlier it is about 37.7%. It goes roughly here. Okay. So, but the thermal efficiency is substantially improved to 37.7%. So, as we increase the reheat pressure, the thermal efficiency is increasing, but and by having a lower exhaust gas temperature. So, further increases in reheat pressure would give slightly higher efficiency, but the exhaust gas temperature would also be reduced below 600 degrees Celsius, resulting in a less efficient steam cycle. With a reheat pressure of 13 bar, the first turbine has a pressure ratio of 2.284, while the second has a pressure ratio of 12.23, differing markedly from the equal pressure ratio we assume at the outset. This example illustrates some of the problems that arise when a gas turbine must be designed for more than one application. So depend on the application. So the gas turbine engine designer must decide what are the best situation, whether to increase the pressure for combustion chamber or having a less efficient steam cycle. So if the cycle pressure ratio will increase to increase the efficiency of the gas cycle, however, the exhaust gas temperature would be decreased, resulting in a lower steam cycle efficiency. Right? So that's all. And what I would like you to do, to go through all the three examples to make sense of the calculation. For example 2.1 just now, I would like you to try with a higher pressure ratio and a higher temperature inlet the temperature inlet temperature, the turbine inlet temperature, sorry, TIT. So and try to go through back example 2.2 as well as 2.3. Thank you very much. Have a nice day. Okay, stay safe. Assalamualaikum warahmatullahi taala wabarakatuh.
Waalaikumsalam. Thank you, Dr.
Waalaikumsalam. Thank you, Dr.
Thank you, Dr.